So welcome to 6.4. I wanted to give you an overview of the central limit theorem. The central limit theorem is pretty powerful and really unlocks the rest of the book, but it's going to be working behind the scenes, so you won't really know in the future chapters that you're using it, but I'll try to point out that you are along the way. So I typed out a few things here that I'll just review with you. The central limit theorem is abbreviated sometimes CLT. And the central limit theorem is something you use when you have more than one thing. So stating that, if you were to look back to any of the 6.1 or the 6.2 problems, you'll find that they just dealt with a man being selected, a woman being selected, just one person being selected. But now we're going to be dealing with the group. That's how you're going to recognize on the test whether you need to use the central limit theorem, is because you're dealing with more than one thing. What it does is it helps you find the probability that that group's average is either above a value, below a value, or in between two values. And so the central limit theorem relies upon the normal distribution. And because of that, we're going to be using the table A2 chart. Now, it can be used in either one of two settings. It can be used with any group size if the original distribution is normal. However, its power is in that second statement. You can use the normal distribution and the central limit theorem if the original distribution is not normal and the group size is bigger than 30. So if you don't know if the population is normally distributed, or if you know that it's certainly not, you can still use the normal distribution if your group size is big enough. That's the biggest consequence of the central limit theorem. And so what the central limit theorem says is, if you're dealing with the group, then what's being adjusted is not the mean. So this symbol right here, this is the regular mu symbol that means the average, but we're going to have it be for the group. And so the way to read this is the average for the group. So I'll put the average or the mean for the group is straight out equal to the mean for the individual. And what also it says is that the standard deviation for the group is equal to the original standard deviation for the individual divided by the square root of the group size. So what we're saying is, if you have a group of people, they should tend to the average for the individual when you average them all out. However, they're not going to deviate as far from that average. So really, as you recognize you're in a group setting, you're going to apply the central limit theorem. And as you do, what you're going to do is you're going to take this same mean. You're going to leave that alone, but you're going to get yourself a new standard deviation before you ever get started. And that new standard deviation will be the given standard deviation divided by the square root of the group size. With that adjustment, we would do everything else the same. So, for example, if we had something like this, if I wrote IQ scores, if you remember before, IQ scores were normally distributed. And they had a mean. The mean was equal to 100, and they had a standard deviation of 15. And our new question is going to be this. Find the probability that, how many? That 9 randomly selected individuals have a mean IQ score less than 115. Okay. And so that's what we're going to be looking at. Now notice what we have. We have a group. We have 9 randomly selected individuals that have a mean IQ score. We want them to have a mean IQ score of less than 115. That doesn't mean everybody has to be less than 115. It's just that they balance out to be less than that. And so as we do that problem, what we want to first realize is that we have a group. Now, you know that IQ scores are normally distributed. That means I can have any group size I want. So if I roll back up here, what this is saying is, if the original distribution is normally distributed, you can have any group size you want. Remember, we only use the central limit theorem if there's a group. But if it's not known to be normal, it better be bigger than 30. So I'm okay using 9 because our original distribution is normal. I recognize that I'm in a group setting, and what I say is, well, then I got a mean for the group. And what that is trying to say above right there is that I'm going to leave that the same as 100. But the standard deviation for the group is going to be a new standard deviation. The original standard deviation was 15, but now I'm going to divide by the square root of the group size, which is 9. So the group size is 9. So what is that? Well, that's 15 over 3. And so I get a new standard deviation for the group of 5. So translating what that says is this group of 9 men, when we look at their average is going to be close to 100. In fact, it's going to be closer than any random person could be because they're going to balance each other out. It's going to be within 5 on average. And so we're just going to do the same problems that we did back in 6.2 with these new numbers. So now I draw my picture. The mean's still 100. And I care about being 115 and lower. So what do I have to do? Well, I know what I have to do because I've been through the 6.2 section. I got to find the z-score for 115. Now, I'm going to subtract away the mean, but divide by the new standard deviation of 5. And so what am I getting? Z is equal to 15 over 5. Z is equal to 3. And so instead of getting, what I was getting when I had 115 before of a z-score of 1, I'm now going to get a z-score of 3 because I have a lower standard deviation. And so we'll look that up. We'll look up 3.00, reminding ourselves that it's on the outside of the chart. And when I look up 3.00, I get 0.9987. Well, as you remember, that's the area to the left, and that's exactly what I want. So notation-wise, they would write it like this. The probability that the group's average is less than 115 is equal to 0.9987. There's no need to subtract it from 1 because I wanted area to the left, and this chart gave me area to the left. So 0.9987 is the probability that that 9 individuals' average would be less than 115 when looking at their IQ. And so this is just an example of the central limit theorem, which can be used, utilizes the normal distribution as long as we adjust that standard deviation.